Hello and welcome to this video lecture. So this lecture will be the first of two reviews specifically discussing linear algebra, and this will be the shorter of the two. So let's get linear algebra review written up here. And this will be part one. And then we'll discuss system modeling. And then we will have part two of the linear algebra review. So let's go ahead and start in on this first shorter of the two. And again, the main purpose for this review is just to refresh you on the basic concepts associated with linear algebra, the very most basic concepts. The second review will touch on some basic concepts as well, but these first ones are really kind of more the definitions, so that I have a chance to remind you of what basic concepts, or of those basic concepts that are associated with linear algebra. So we'll start that off with here. We will review those concepts. From linear algebra. Of course, that are important. Specifically for state space or the state space representations that we will be discussing when we start talking about system modeling. And of course, I'll bring in some others that are, and here I'll just say, or are convenient. To discuss presently. Because some of what we'll talk about in this lecture won't really directly relate to the state space, or I should say to state space representations in and of themselves, but we will need it for the second part, some of these concepts for the second part of our linear algebra review. So again, as I indicated, starting with some basic concepts. First of all, a matrix. So of course, we all know that matrices are central to linear algebra. And so what is a matrix? It is a rectangular array of numbers with n rows and m columns. Now we'll discuss this in a bit more detail momentarily. but let's just go ahead and acknowledge for right now, before we investigate this in a bit more detail. So that means that each number, or alternatively each entry, can of course be uniquely identified by the row it is in, I, and the column it is in, J. So here we'll capture it is in within the matrix. So as we can see, it is a means to, or can be viewed as a means of organizing data. Now, of course, we'll soon come to realize that it is a very powerful means of organizing that data, because meaning can be attached to not only the quantity, but it can be attached to the location, general location, and maybe in some cases even the specific location within the matrix itself. So if we have a matrix A, we can then say that we are looking at, well, an entry in a matrix A. We can say that we are interested in looking at the number little a that has a row that is located on row I and column J. So that is one way of referencing that particular number. Or if we choose to, we can just look at what's happening with the overall matrix. Actually, let's go ahead and draw that a little bit bigger. So we can list out everything in the matrix, in which case then we can not only use this means of identifying the location in the matrix, we can also graphically look at what is going on with the matrix and identify, whoops, got a little rambunctious there, that's still row 1, and identify the value that way. And we'll have our second row here. And A2, 3, all the way out to A2M, and then AN1, AN2, because this is row N, AN3, all the way out to ANM. And we'll give ourselves just those 3 dots. So there we go. So that is another way that we can look at what's happening with this particular set of data. So, oh, sorry about that. Don't know why my computer screen got as rambunctious as it did there. If you can give me one moment, still trying to size it properly. It's just getting fussy with me. Too big, too small, hopefully just about right. Okay, so with that, as an example, a very simple example, if we have A being 1, 2, and then in the next row 3 and 4, if we were interested in finding A21, that means we're in the second row in the first column. That of course puts us right here. And so A21 would be equal to 3. Now, of course, if we are dealing with some kind of computer software, we certainly wouldn't necessarily have the ability to go in and look at a particular location in the table. We would just hopefully know that that's the particular entry we're interested in. And then we would give the proper indexing or provide the proper indexing to the computer program that's being run, and it would be able to select the appropriate value for us. So as you can imagine, there we are. Want to make sure I keep my indentation correct, or I would say consistent might be a better word. So the properties, of course, of a matrix are determined of course by the values themselves. I'll add that on later, or actually we can capture it now, not only by the collection or set of numbers that we're dealing with, of course, in the array. I got a little messy there. Let me redo that. So clearly the properties are going to be, the properties of that matrix are going to be associated with, again, that set of numbers that we have associated with that matrix, but it's also, their position in that matrix. So we can't just take any 4 random numbers and stuff them into this A I have in my example here and expect the values to, or the properties of that matrix to necessarily be the same, or even go and reorder, take those random numbers and then put them in one, organize them in one way and then go and organize them in a completely different way and expect the properties to be the same. So it's important to recognize, but the location. So here I will say, but also their location will determine a significant number of the properties associated with the matrix. And so when I say specific location, I really mean their specific entry in the table in that rectangular array. So now let's start talking about some of the operations associated with matrices. So first, let's start with probably the simplest operation we add to matrices. So when adding two matrices, and we can have two matrices, A and B. And of course, the notation that we use for that will simply be an extension of our addition notation for scalar quantities, A plus B. We get a new matrix. Yeah, let me get rid of that extra dot. So a new matrix C will be formed. That is simply the sum of the corresponding elements of A and B. So another way we can write that, and here, instead of EG, let's use IE. Cij is equal to Aij plus B ij. Where, of course, I goes from 1 to, let's do an equals rather than an arrow there. I think that would be a little bit better. So I is equal to 1 to n, and j is equal to 1 to m. So of course, that means, and so here I'll start that with consequently. Clearly A, B, and C, because now that we have this rectangular shape associated with the matrix, not just a single number anymore like we had back in our scalar days, we need to impose additional limitations on what we are allowed to do with these particular entities. And so we can see that A, B, and C very clearly must all have the same size. Now, that is for us here talking about math and engineering. If you go into MATLAB, MATLAB does some interesting things, has some interesting conventions that are not generally recognized mathematically. And one of the things that it quite likely will do, I'd have to double check this, but I think I noticed it back in the day, is if you add two matrices of different sizes together, it would just assume the other entries in the quote unquote smaller matrix, if I can, I know that's not a completely proper way of saying it, but in, or let's say it this way, the entries that exist in one matrix would be added to fake zero entries in the other matrix that weren't present. And so it would just go ahead and translate those values over to the final matrix in an unaltered fashion. So understand that's not a universally recognized convention though, even though that's potentially what MATLAB, if I'm recalling correctly, let me just say it that way, that MATLAB does. So just be careful with that. So as an example, and again, you're going to see that I have some favorite entries that I like to use, because here A is again going to be 1, 2, 3, and 4. And then completely shockingly, B is going to be 5, 6, 7, and 8. So when we add those two together, what do? these two matrices together, we take the corresponding entries, A1, 1, and we add it on to B1, 1. And so we get 1 plus 5 is 6. And so we would get 6. And then A1, 2 plus B1, 2, we would get 2 plus 6. And of course, that's simply going to be 8. And then we just keep going on through. 3 plus 7 is 10, and 4 plus 8 is 12. Now, of course, I'm using A, B's, and C's as names for my matrices. That's not necessarily a general way of naming matrices, though you will see that we do like to use A's, B's, C's, and D's a lot in this class. Okay, so one thing that can be seen very simply is because you can add any numbers, any particular set of numbers in any order, we can see that A plus B would equal B plus A. So there's no issue with changing the order of adding matrices together. Now, of course, one of the things that we do with pretty much anything after we finish talking about addition is talking about multiplication. Now, of course, you might think, well, Professor Densmore, hey, we normally talk about subtraction. Well, what's subtraction? That is just going ahead and, as we will soon see once we talk about multiplication, just multiplying one matrix through by a negative. If we wanted to subtract, you just multiply one matrix through by a negative 1, and then you just add. So there's really no need to talk about subtraction, since we can capture subtraction with the first topic we're going to cover when we discuss matrix multiplication. So when multiplying a matrix A by a scalar, and here we'll call our scalar alpha, by a scalar alpha, a new matrix and here we'll call that matrix B, will be created where each element of B is the product of alpha and the corresponding. So that element will have a corresponding element in A. So we'll say, and that corresponding element of A. So here we have that Bij, which of course is one element in B. Aij is the corresponding element in A, and we just go ahead and say whatever element in B that we're looking at, we go look at the corresponding element in A and we multiply it by that scalar alpha. And of course, again, I is going to go from 1 to n, and j is going to go from 1 to m. So that, of course, that means, and we do that without skipping any numbers or anything else. So it's inclusively between 1 and n and 1 and m, of course, going in, using integers. So that means that, of course, that would ensure we capture every element in A and then map that to a value in B, where that mapping is quite simple. It's just multiplying the value of in A by alpha. So we can immediately see that much like addition, we have a property associated with the size of the resulting matrix, which is that A and the resulting matrix B must be the same size. And so, of course, as an example, if we have alpha times A, and shockingly, A is going to be 1, 2, 3, and 4. So now the big reveal is what I'm going to use as a scalar. Hey, why not? Let's use the value 2. And so then we can see that 2 times 1 is just going to give me a 2 over here for B. 2 times 2 is going to give me a 4. And then pretty clearly 2 times 3 is 6 and 2 times 4 is 8. And so that will be my matrix B. Now, since it doesn't really matter whether I multiply 1 by 2 or 2 by 1, or for the first entry, of course, here. And since it doesn't matter whether I multiply 2 by 2 or 2 by 2, which clearly is kind of a fairly interesting thing to say, or multiply 3 by 2 or 2 by 3, we can see then it doesn't matter the order in which we multiply. Sorry about that. The order in which we multiply the matrix by a scalar. So here we'll just say note, of course, that alpha times A is equal to A times alpha. And so that allows us to go ahead and change that order. And in most cases, just by convention, I almost always see the scalar being first and the matrix being second. So that's one thing that you will almost always see. And so we'll generally reorder things to make sure that we end up with that particular sequence in the equations that we might be developing, or that we might develop or be working with. Now, as you can imagine, now that we're dealing with more complicated entities in the form of matrices rather than the algebraic values that we had, as which are scalars, that we would add and multiply. Clearly, since these matrices are more complicated, that means that we can define substantially different ways of operating on these matrices than we would ever be able to figure out for standard scalars. And so it turns out that there are multiple ways of multiplying. So this idea of multiplying a matrix by a scalar, that's essentially the closest algebraic equivalent to multiplying two things together, two scalars together that you had in algebra. So now multiplying a matrix by, instead of a scalar, but another matrix, clearly things are going to have to change, because now we're taking two very complicated, well, I wouldn't say very complicated, but two more complicated entities, and we're trying to multiply them together, because it would be kind of a little bit of a letdown if we just go into linear algebra and all we can do is take our algebraic mathematical operations and just extend them to an entity that is just an array of numbers. So that would be a little bit of a letdown. So let's go ahead now and define a different way of multiplying things, specifically multiplying now matrices themselves, which of course means then that we wouldn't be limited to just multiplying matrices by scalars, which again would be pretty limiting and would be a bit of a letdown. So when multiplying two matrices, and here we'll say that the two matrices that we're multiplying together are A and B. So then we can go ahead and write this in a particular form. So this will be written as AB. We get a new matrix C, let's go comma C, comma, will be formed where each element of C is a linear combination. Oh, wait, remember, this is linear systems. And so now we're talking about entries in C being a linear combination of all the elements of each row of A with all of the elements with each of the now columns. Somehow an S turned into an E there, my apologies, with each of the columns of B. And so we can start to see how these terms keep coming together: linear algebra, linear combination, linear systems. And so clearly, if we are dealing with some kind of representation that exists in our engineering world, we certainly wouldn't want to go choose a completely misaligned mathematical representation. It just wouldn't work well. And so, you know, again, that's why we're studying this idea of linear algebra along with this idea of linear systems, because of course, linear algebra is the perfect fit for this idea of what's going on with linear systems theory. And to some extent, you might say, you know, linear systems theory was essentially created in a way to fit well with linear algebra. And I certainly wouldn't argue with that statement or that sentiment, because as you'll see, when we start getting into linear systems theory, when we start getting into our system representations, specifically our state space representations, you will see that there was effort taken to work within the structure of linear algebra. And so I think that will become pretty clear in the lectures that immediately follow this sequence of lectures associated with part 1 here. Okay, but please bear with me, and you'll see that soon enough, but we won't see that necessarily in this particular lecture. Okay, so what does that mean? That means, I want to see, because we're talking elements in matrix C. So Cij will be equal to AI1 B1J plus AI2 plus, times BB2J plus all the way on out, all the way on out to AIM and BMJ. Now, of course, again, since I can't have it on the same line, I'll just do the where here, where I is equal to 1 to N and J is equal to 1 to M. Oh, my apologies, 1 to P in this particular case, because we will levy an additional requirement on here. My apologies, I got ahead of myself. Okay, so let's go ahead, and just as we have before, we've discussed the sizes of the matrices involved in a particular mathematical operation. And so we can see that A must be an N by M matrix. B must be an M by P matrix. And last but not least, that means that C will be, the resulting matrix will be N by P. And you can also see what I mean by a linear combination, where we have these elements associated with a particular column, specifically a column in B, and we're multiplying those entries by these values that are in a row in A, and we're summing all those together. So you can see exactly where this idea of a linear combination is coming from, just a linear combination between very specific subsets, or a very specific subset of values in A and B when we're looking at one particular value in C. So again, we can look at a quick example where we have A and B. Again, I'm going to stay with my same A as I have in the past. And so we'll have 1, 2, 3, 4. And now B, of course, will be my 5, 6, 7 now. 8, 9, and 10 to just show that you can multiply matrices of different sizes together. So A times B, or sorry, A is a 2 by 2, B is a 2 by 3. And so notice that these M's must be the same. And sure enough, here we have the same M. And so we can say that that equals C. And so here I'll just go ahead and write out C so that way, because this is a more complicated operation than we've encountered so far in this class. So what I'm going to do is I'm going to take the first row in A. So I start with this one and I multiply it by the first column in B. So 1 times 5 is 5. And then I added on to the second entry in that row multiplied by the second entry in the column. And so that's why you can see the final 2 here must be the same as the leading 2 for B. So that way, whatever the number of entries I have here in A for the row in A is the same as the number of entries that I have over here for a column in B. So then 2 times 8, of course, is just going to be 16. So I get 5 plus 16. Going ahead and just doing one more. Let's do this one down here. This value in C, where we will have then, and one of the things is you can see, of course, that I have the first row, the first column, that gives me the first entry in C, the 1 by 1 entry in C. So if I want the let's say it this way, the value in the second row in the second column, the C22 value, then I would just simply take the second row in A, I would take the second column in B, and I would form that linear combination. So 3 times 6 is 18. Oh, I don't know why I wrote it small, my apologies. So 3 times 6 is 18 plus 4 times 9, which is 36. And that would give me that particular entry. So I'm not going to go in detail through all the entries. I think you guys can multiply things out, but I'll just go ahead and for completeness, write them all out here. So the second entry in the first row for C would be 6 plus 18. Then the third entry would be 7 plus 20. Then going to the next row, we would have 15 plus 32. And last but not least, for the last entry, we would have 21 plus 40. And so, of course, that means that in the end, C would just be 21, 24, 27, 47, 54, and 61. And so then you can see that here we start with N, here we end with P, and so C turns out to be an N by P matrix. Of course, for us, that would be a 2 by 3, and that's exactly what we have here. Now, it's important to recognize, though, and I guess we'll put it as a little note underneath this example, but a very important note, is that you can see that since we're forming linear combinations, A times B in general does not equal B times A. So reversing the order is something that if we are going to do it, we have to be very certain we know what we're doing and that we're doing it properly. So don't just idly go reverse the order, because in general, you're going to end up with a different result. And that's if you end up with a result at all. So here you can see immediately what I'm getting at Actually, let's do an EG here. So if I go ahead and reverse my A matrix and my B matrix that I had up above, I have 5, 6, 7, 8, 9, 10 times 1. Writing 1 while trying to write 1 while I'm thinking of 2. 1, 2, 3, and 4. And we can immediately see that this just is nonsensical, because trying to multiply the first row by the first row of B by the first column of A, because that's exactly what the order means, we of course can handle what's going on with the first 2 entries in each. We have a 5 times 1 plus then a 6 times 3. And then we are going to try to add on 7 times, who knows what, right? Because we, of course, ran out of entries in A along that particular column. And so, of course, this is not valid. Double underline, double exclamation. So we, of course, can see that there's just no way that we're going to end up with a proper multiplication or yeah, let's say it, a proper multiplication, matrix multiplication operation. And we can see that we could have seen it, of course, and we already knew it was going to happen, because we have a 2 by 3 here, we have a 2 by 2 here. And of course, these values for a proper matrix multiplication operation, those two have to be the same, and we can see that these are different. So this is B, this is A, and this is different. And so, of course, that means that things weren't going to work out very well. Okay, so I know that I went to some length to discuss it before, but because it is so crucial, I do want to discuss again, and actually more than discuss it, bring it in very formally, that this idea of matrix multiplication might seem really bizarre initially, because you might be looking at it and thinking, why would anybody ever try to formulate a multiplication approach like that? So here I'll just say matrix, this form of matrix multiplication is, of course, the perfect tool, perfect mathematical tool to capture linear combinations of elements into matrices. And so, of course, when we're talking about linear combinations, that's just saying that I'm taking one value, multiplying it by another value, and then summing it to another product of 2 related values that are somehow related in some particular way to the first values, etc. And so, of course, the relationship that we're talking about here is associated with the position, the appropriate position in the matrix. So here we'll just say that C11, of course, was equal to 1 from matrix A times 5 in matrix B, specifically 1 in the first row of matrix A and 5 in the first column, matrix B, plus 2, the second entry in the first row of matrix A times 8, the second entry in the first column of matrix B. And then C21, of course, was equal to 3 times 5 plus 4 times 8, where 3 came from the appropriate position in matrix A, as well as that 4, and the 5 came from the 5 and the 8 came from appropriate locations in matrix B. And so these are, and we could of course go through all of them, these are linear combinations. So that hopefully gives you a better understanding of what's happening with matrices. Well, first of all, what a matrix is and how we can work with some of the basic mathematical operations associated with matrices. So with that, we'll go ahead and call this first part of this video lecture a wrap. And when we come back for the next part of this particular linear algebra review, I'll be bringing into the picture this idea of what are called vectors. Now, I'm sure you've already been exposed to vectors, but it's always a good idea to reintroduce things so that we can start reframing these very familiar things in a way that makes sense for linear systems theory. So hopefully you started seeing that already, this idea of linear combinations. And of course, linear combinations will be central to what we're talking about when we start looking at linear systems theory. So with that, I will call this first part of our video lecture a wrap. And when we come back, I'll probably just pick right back up on this very same OneNote page. So with that, we will call it again a wrap.